Okay, here's the system of equations we got for the second network. And that looks kind of daunting, but it really is not half bad. Okay, what would you do? You should think it through. What's your strategy for solving this? And let's do it without without reducing a matrix. Let's go ahead and solve it in the most basic way. And I'll observe that when you get into systems this size, if they get much bigger than this, especially, you're probably just going to write the whole thing out as a matrix equation and solve it using a click of the mouse or a push of a button. Okay, it's just a simple matrix equation in 5 variables. Okay, any case. Okay, you should have paused and thought about it. Now the way I'm going to do it, I'm going to solve for I5 up here and using the first equation. And one reason I do that is I don't see any I5s down here except in this equation. So between these two equations, solving the first equation for I5, it's I1 plus I2. Second equation, I4 equals I5 plus I6. So I5 is I1 plus I2, so we got I1 plus I2 plus I6. And now we have expressions in terms of the other variables for I5 and I4. Okay, so now we have 4 equations in which we can substitute for I4 here, 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 and we don't really have to substitute for I5 in any of the equations. So what do our new equations become? Do that off camera. You should think that through. Okay, now what you did might be somewhat different than what I did, but all I've done here is now I've taken the third equation and I've substituted I4, which is I1 plus I2 plus I6, so that I'm going to have negative I1, which will take care of this I1, so there won't be an I1, and a negative I2 from I4, so there's a negative I2, and negative I6, here, and I have that as a positive, so I better be careful about that. And then I have my I3 from here. Okay, so that would be this equation substituting for I4. This equation has an I4, it's negative 25 I4. If we divide through by the ohms, this becomes an amp, and we just get pure numbers in front of these. We're going to have negative 25 I4. Well, negative 25 I4 is going to give us a negative 25 I1, which combined with a negative 15 I1 gives me a negative 40 I1. Now I'm also going to risk changing all the signs, so these all come out positive. So changing the sign, that comes out 40 I1. Then I have 25 I4, so I'm going to have 25 I2. Well, that's just going to give me a 25 I2. Okay, and I'm going to have a 25 I6. And now I've taken care of my I1 and my I4, and my 10 volts is going to, well, now it's 10 amps since I've divided through by ohms. It's going to go on the other side. That would become a negative, but since I'm reversing all the signs, I've got this. So I've done a couple of things there, but you should convince yourself either that I'm right or I'm wrong. When I substitute for I4 in this equation, this is what I get. Okay, in the next equation, we have I4 again, and we got a 25 I4 divided by the ohms. And that's going to give me 25 I1, 25 I2, 25 I6, and the 25 I2, I3, the 10 I3, I'm sorry, the 10 I3 that I have here. The last equation has no I1, has no I4 and no I5, so that's simply it. So I now have a system of 4 equations and 4 unknowns, which is a lot better than having 6 equations and 6 unknowns. These steps, if you write them out carefully, can actually be done pretty quickly. Okay, in my next step, I started to solve for I3 in terms of I1, and I got negative 5/7 I1, and then I realized I'd be multiplying these things by fractions with the denominator 7, which would be a lot messier than multiplying by things that have denominator 5, because everything here is divisible by 5, so I'm going to cross that out, and I'm going to say, well, I1 equals negative 7/5 I3. Okay, that's very obvious. Now, if I plug this into all these equations, and actually I'm going to only have to plug it in to 2 of these equations, it's going to give me 2 equations and 2 unknowns. You notice I have 3 equations and 3 unknowns. Plugging this in will eliminate I1 from these equations, giving me 2 equations, just I2 and I3. So go ahead and do that and see how it works. Okay, not sure where I left off, but I'm sure I got this. I1's negative 7/5 I3, so that plugging that into the first equation will give me negative 7/5 of 40, which is negative 56, if I did my arithmetic correctly. I3 equals 10 amps, and that's going to lead me immediately to a solution for I3. It's going to be, oh heck, I've got a sign problem here. It's going to be negative 1056 of an amp. It's going to fix what I did up here, but we'll fix that. And then we got same thing, substituting this in here for I1, we're going to end up with negative 31 I3. The 7/5 of 15 is going to give me negative 21, and then I got a negative 10 I3. That's negative 31 I3 minus 20 I2 equals 0. We will solve for I3, so we plug that in here, and we get a result here. And then we use this result. We solve this easily for I2. We get this, except I'm going to have to change it a little bit. And then what can we do? Now we know I2 and we know I3. We can go back here and solve this one, let's say for I1, yeah. And that actually solve this one for I1. Okay, since we know I3, we very easily get this, and we continue just moving back up the sequence and back substituting wherever it's convenient, and we'll quickly get the remaining variables. Now they're going to get a little messier. The fractions are going to get a little messier, and we do want to try to do this with 100% accuracy. We don't want to round off anything, because round off errors can magnify very easily in a situation like this. Okay, I've corrected the sign here. I3 is going to be negative 1056 of an amp. Substituting that into this equation, negative 10 times negative 31 is plus 310, so we got 310 over 56 amps minus our 20, I2 equals 0. Solve that for I2. We're going to divide this by 20. 56 times 20 is 1060. Good heavens, that's not right. Hang on. Okay, it's 20 times 56 is 1,000 plus 6 times 20, which is 1,120, not 1060. So here's our I2. I1 is just a simple multiple of I3, and here I've got I3, so I just multiply that by negative 7/5. The 5 in the denominator divide the 10 to give us a negative 2 times negative 7 is going to give us plus 14, and leaving the denominator unaffected, 14 over 56, which turns out to be a nice number, 1/4 of an amp. Now that we've got I1 and I3 and I2, we can go back, get I6 if we like. We have I2 and I3, and then having I6, we can use what we know about I1, I2, and I6 to get I4. Now I'm not 100% on my arithmetic is correct. I'm doing some really dumb stuff here. So you can check me on this, but you see that the process is not difficult. We can also build up our augmented matrix for the original system. And I've done it for the first row. We have, now I've gone ahead and changed the sign so that I1 and I2 will both have coefficient 1, so we get 1, 1 here. We have no I3 or I4, so we have zeros there, and we're going to have then a negative for the I5, having changed the signs, and a 0 and a 0. And for the second equation, what do we have? We just have an I4, an I5, and an I6. We might as well leave the signs as they are. We have no I1, I2, I3. We have an I4, we have a negative I5, and a negative I6, and a 0 on that side. So write out the rest of the augmented matrix. I'll write it out, and we'll see if we agree. I just realized I'm off the screen over here. I can't keep this here and this here. Again, what I did was I multiplied this by -1, and then I put the coefficients in order. I'll have a 1 for I1, a 1 for I2, zeros for I3 and I4. They don't occur, nor does I6. And the I5 will have coefficient -1. So now I can show you the first row of the matrix. The 1 for I1, the 1 for I2, the -1 for I4, zeros every place else. Now, I recommend that you go through and write out the rest of the matrix without looking at what I've done, and then we'll talk about how we would begin to manipulate this matrix, just to give you a little refresher. Okay, what I see when I look at this matrix, I see a lot of zeros and ones. That's always cause for joy. I see this row here. I have a 1 here and 3 leading zeros. Well, I would move this down to the 4th row and move the 4th row somewhere else, probably up here, just do things one at a time. And I would then have a 1 on the diagonal. I want 1s in my diagonal, and I would have it here. I know I'd have a couple of numbers over here that I'm going to have to deal with later, but for now, that's pretty good. Okay. Also, I see here that in subtracting the first row from this one, I'm going to get rid of the 0 here very easily. I'm going to have a -1 here. Well, I move that up into this position, and it gives me a nice row for the second row. I see that I have 2 leading zeros here and a 10. Well, I divide through this row by 10, giving me a 10 here and a 2.5 here. Move that into the third position and move something else down, so that I would have convenient rows for my first 4 rows. And I could use what I have in those first 4 rows to wipe out anything that I want underneath. And if you understand the process, you understand what I'm talking about. And if you don't, run through it, review a little bit, because certainly you did a lot of row reduction in prerequisite courses, especially in linear algebra. So I'm not going to do the whole solution. The solution we get using this should agree with the solution we get with this. It's a mess, but you need to work through it and really understand it, so that then later on when you use technology with matrix operations, you'll know exactly what they mean and what they're doing.